Hello and welcome everybody back on my channel. This is going to be a short video where we'll demonstrate something that I implemented for the compiler over the last few days. So as you might know, I've been working on my own compiler for the past 3.5 years at this point. It is written from scratch. It is written for a language that at this point you could call a low-budget version of Jonathan Blow's new programming language, which is why we titled it Lidl-Jai as a kind of joke. I'm not affiliated in any way with the real language. This has just been a hobby project that over time has developed into something that is actually usable, at least for my personal use cases. And I'm actually working on a game in that language, as you might see in my other videos. But today I'm just gonna showcase, a tiny feature that I implemented. So the feature itself has been in the language for a while, but today we're going to talk about how I extended that and made it a little more user-friendly. So in this language, we have some runtime checks. So we provide, or you can, as a user of the language, you can enable certain checks that you want to do at runtime. These are, for example, overflow checks, where we check, hey, is the result of this expression, does it actually fit into the target type? So for example, this would fail. We have range checks, which are similar, where we check when you downcast a primitive integer, does the value actually fit into the target type? We have bounds checking for arrays, which is pretty common. And we have one more specific thing where we check if the underlying type of an any value actually is what you cast it to. So this is kind of specific to the Jai or Lidl-Jai language. But yeah, this can also by you, basically. So we provide a check for that. And these runtime checks have been in my compiler for a while. I would say a few months or maybe even years. But until recently, they would just issue a debug break statement or instruction. And that debug break instruction would basically tell the debugger that you're running in, hey, I actually found like a breakpoint here. It's kind of like a breakpoint. It halts execution, and then you can, step through the call stack. You can investigate what's happening and so on. But if you're not running inside a debugger, this instruction would basically terminate your program. And so that's kind of annoying, because when you're running the program and then any of these runtime checks fail, your program would just stop and you wouldn't know why. And you'd have to step into a debugger and do all that. And so what I implemented now is I actually added some nice error messages that get printed out when any of these checks fail. And so we can basically see that here. So I executed this program in debug mode, but not in a debugger. And it tells me, hey, there is actually an overflow that occurred in line 11, right, which fits to this line here. And it says the data type U16 overflowed, because this, well, is a U16. And so now at least I know where in my program this check failed, and I have some more information about what exactly happened. And if we run this inside a debugger, we can also see, hey, we actually hit this debug break instruction, which is this one actually in 3, and we can now step through the call stack and we can see, hey, this failed, and I can investigate, hey, x, well, okay, x is actually a pretty big value, and x plus 1 will actually overflow this. And now I can obviously also keep going, because this failure isn't fatal. We can just continue as normal. These runtime checks just usually indicate that, hey, this is probably not what you intended. If you did intend this, then you need to be explicit about that. And so, for example, in this example, you could say, hey, I'll do a modulo operation on this to ensure that whatever the result is, I manually adjust it to the target range. In this case, for example, we are assigning a S16 to a U8, and this is out of range. So this could be a nasty bug where you're like, oh, this value is correct, but then at some point I assign it to something, because obviously this doesn't have to be a declaration. You could have something like this, and you're like, what happened here? Why is y not equals to x? Well, this might be y. And so if you're like, hey, I know this might happen, that's fine with me, you could say, hey, I explicitly cast this, and for explicit cast, we don't insert this because we assume that you as a programmer accept that this can happen and that is intended. And so we go further here. Now we have bounce check. This, most people would probably know from most modern programming languages. We have an index of -1, which, can lead to just reading garbage data, or it could actually lead to a seg fault, whatever. At least it's undefined behavior. We have the same for if the index is 5 instead of the limit would be 4. And this is the last check that I mentioned. So basically we have an any value, which is, I think there's also std any in C++, although I'm not too familiar with that. But this any value actually internally is an F64 in this case. Why? Because we pass 5.0 to it. So that's a double value. And we attempt to cast it to a U16 here, which just, can again lead to garbage data being read, because this cast is basically a mem copy. So if I was trying to be explicit about this, I could say, hey, first cast this any value to a F64. So we're basically unwrapping this value, and then do an actual primitive cast to this integer value. So this would again avoid this runtime check. But if you forget that, then we got you. Yeah, so that's basically what happens. These messages, they also show the call stack, as I mentioned, which is really nice because you can quickly see, hey, where in my program did this actually occur? These are also implemented in the C backend. So the compiler has its own ext4 backend, and it can also compile to C. And this check also works in C, or in the C backend, I should say. This is a little bit different because when you're working with the C backend, we are no longer in control of the source information. So it's a little bit harder to actually understand where the crash occurred, but you can still do it. And so this also works on Linux, obviously. I took care of that. So if we also do this, we can actually see the exact same thing happening, which, you might expect, but it's nice that works out of the box for the compiler. So now I'll just quickly go over how I actually implemented that. Basically, the compiler inserts bytecode instructions. So if you don't know anything about compilers, this might be a lot. So I recommend watching different videos on that first. But here we can see this is the bytecode generated for the main function. So we can see we have some constants here that are familiar from the source code that we just looked at. And here, for example, we're doing this range check. And so we're basically checking, hey, does this value actually fit into our target? And so we're checking, hey, so R6 is the value that we want to cast. This is the input value, and then 0 is like the minimum value that we support in this new data type. 255 is the maximum value because we're casting into a U8, an unsigned byte. And so this range check is implemented in bytecode, and then the x64 backend would then replay or implement this range check by doing some comparisons, right? So we're basically comparing this value to 0 and to 255. And if that fails, then we will actually call a C++ function that I implemented. That would be this one. So runtime support range assertion. And this just takes these arguments, which are basically implemented in the instruction, right? These are the operands of the instruction. We're passing them to this function, and then this function can actually do, the stack tracing, the nice error formatting, and so on. Why is this in C++? Good question. Can definitely also be in the Lidl-Jai language. And looking back at this, it might have been better to actually implement that in Lidl-Jai, but this works. The reason why I did it is because I actually compile this as a library, and then I can include that library in everything that the compiler actually compiles. So it's an implicit library of the compiler, which means that programs written in Lidl-Jai don't have to actually compile this. And they don't have, to include all the headers and everything. So compilation should be a bit faster. That's why it's in C++, although again, might have been a mistake. Maybe I'll port this to be actually in Lidl-Jai in the future, but we'll see. So this is kind of this new functionality. So whenever we run into a crash, we can quickly see, or it's not even a crash, but if any of these runtime checks fail, we can quickly determine, hey, okay, this is actually what happens. And that makes debugging way easier. Okay, so that was a quick demonstration of this new feature. I hope you enjoyed it. If you have any questions, just let me know. Also, I do stream on Twitch occasionally, working on either the compiler or the game. So if you want to check that out, feel free. Thank you and goodbye.